Okay, let's get started. Good morning. Okay, today we're going to look at section 15.9, continuing with triple integrals, but this time in another new coordinate system, what's called a spherical coordinates. All right, so what is spherical coordinates? It's another way to describe a three-dimensional location. By three numbers. The first number is the lowercase Greek letter rho. Looks like a P, but it's not a P. It's rho, theta, and phi. And I'll show you what these things are. Rho is a distance, and theta and phi are two angles. Rho is the distance to the point from the origin. And rho is always considered to be positive. Theta is the angle from the positive x-axis to the projection of the point onto the xy plane. And this is the same as the theta in polar or cylindrical. Right? It's the same theta we've seen in these two other coordinates. The last one, Greek letter phi, this is the angle measured from the positive z-axis down to the xy plane. I'll draw a picture in a little bit. All right, so here we have two angles and one distance. In Cartesian, it's three distances. In cylindrical, we have two distances and one angle. Here we have two angles and one distance. It's just another way to describe the point. Okay, so suppose our point is right here. First thing we're going to do is to project it down onto the xy plane, the shadow of that point. Let's say the shadow is right here. The angle theta is measured from the positive x-axis to that location. So this is theta. Like I said, exactly like the cylindrical or polar coordinate theta. Exactly the same thing. The angle phi is measured from the positive z-axis to that location. So coming from the positive z-axis, we measure the angle phi downward. So that's phi. And lastly, the simplest one to see is the distance from the origin to that point. That's rho. So from here to here, that's rho. Okay? By convention, we always consider rho to be positive. We let theta go from 0 to 2 pi, but we only let phi go from 0 to pi. The reason is if you want to have every single point in a three-dimensional space, you only need to let phi go from here to the negative z-axis, because theta will take you all the way around to get all the points in that space. So theta is we let theta go to 2 pi, but we don't let phi go beyond pi. If you go beyond pi, you're going to overlap and get some of the points that theta will eventually get you on the back. Okay, so that's the basics of the spherical system. Let's look at how we convert this from Cartesian to and from. First, we'll look at conversion to Cartesian. Given rho theta phi, how do we recover x, y, z? So first of all, let's take this green triangle here, dotted triangle. Let's bring it out and take a look at it. So this is the green triangle from the last page. This is the z-axis. And remember, phi is measured downward like that. From trigonometry, we know that this is also phi. We know the hypotenuse of this is rho. That's where our point is sitting. And let's call this distance down here, let's call that r for now. All right, so from this view here, this right here, this is z in the Cartesian. So we're looking at that triangle from kind of the side of that triangle. The distance measured from the xy plane up, that's z. So z should be pretty easy to figure out from this triangle. Here's phi, here's z, and rho. What we can do is to do a cosine. Note that cosine of phi is adjacent over the hypotenuse rho. So this tells us that z is equal to rho cosine phi. All right, so that's the first Cartesian coordinate we can recover from rho phi theta from that picture. From here, let's also figure out r. If you do a sine here, sine of phi is opposite over hypotenuse. So r over rho, which means r is equal to rho sine phi. And on the previous picture here, this one here, this distance on the xy plane, this is r. And this is x, of course, and this is y, right? Now let's take that triangle that's lying on the xy plane. This is r. This is theta. This is x, and this is y. Right? So that triangle that's lying on the xy plane. I yanked it out, and we'll be looking at it here. We'll do a little bit more trick here to figure out x and y. So from this picture, again, let's do cosine. Cosine of theta is adjacent over the hypotenuse. Oops, I got it backwards. Sorry, x over r. But from above, we knew what r was. R is rho sine phi. So this means that x is equal to rho sine phi cosine theta. Now that gives us x if given rho phi theta in spherical. And very similarly, we can figure out y from that picture. Sine of theta is equal to opposite over hypotenuse. So it's y over rho sine phi, because r is rho sine phi. Therefore, y is equal to rho sine phi sine of theta. Now here are the formulas that you will need to know to convert from spherical to Cartesian. And here's one more identity that's useful here. If you add all of these things squared together, x squared plus y squared plus z squared, you get r squared, rho squared, sorry. So that's not very useful when converting from spherical to Cartesian, but this is useful when going from Cartesian to spherical. Okay? All right, let's try this out on something. Here's a point in spherical. The point is 1 pi over 3 pi over 6. Let's figure out what it is in Cartesian. Remember the order these things are given. The first one is rho. That's the distance from the origin to the point. The second one is theta, the angle on the xy plane. And the last one is phi, the angle measured from the positive z-axis down. And let's first locate this point so we can get the quadrants for theta correct. All right, pi over 3, that's the angle on the xy plane. So pi over 3 right over here. Notice we start with the xy plane here. That's where we locate the shadow of that point. It's kind of like if you're looking for something in the sky, but you see you can't see it yet, but you see the shadow of that. You look for the shadow and you look straight up to find that thing you're looking for. So first we found where the shadow is. The shadow of the point is somewhere over here. And then to look up, pi over 6 from the z-axis. So the point is way up here somewhere. And it's measured pi over 6 downward from the positive z-axis. Finally, the distance from the origin to that point is 1. All right, now the formulas in the boxes, those are very useful now. Either you do trig again or you just use the formula. If you memorize them, great. If not, just do trig with the triangles you got here. Not terribly difficult. But here are the formulas we just discovered. All right, x is equal to rho sine phi cosine theta. So rho is 1, simple. Sine of phi, what's sine of pi over 6? Sine of pi over 6? 1/2. Very good. Cosine of pi over 3? Gotta be quicker than that. You gotta know this stuff. Cosine of pi over 3? 1, yep, 1 over 2. So this is 1 over 4. That looks right. It should be positive. So looks good. Y should also be positive because we're dealing with the first quadrant on the xy plane. So that's a way to check if you have the right number, at least the right sign. If the sign is wrong, then it's wrong. If the sign is right, then you have a chance to be right. All right, so rho sine phi, sine of pi over 6, again, is 1/2. And then sine of theta, sine of pi over 3 is root 3 over 2, right? If you know one of them, you know the other. So that's root 3 over 4. Z is rho cosine phi, so 1. Cosine phi, cosine of pi over 6. Right, root 3 over 2. So there we go. Another way to check is using the last formula on the previous page. We know if I add the sum of the squares of these three things, I should get 1. I should get rho. So this is 1 over 16 plus 3 over 16 plus 3 over 4. That's 12 over 16. 12 plus 3 plus 1 is 16. 16 over 16. That's equal to 1, which is r squared. So that's good. That tells us that x, y, z must be correct. And therefore, in the Cartesian coordinate, our point would be at 1 over 4, root 3 over 4, root 3 over 2. All right? Now let's go the other way. Let's start with a Cartesian. Let's go to spherical. This is the more dangerous one because you're recovering angles. And when you're dealing with angles and trig functions, quadrant ambiguity is always there. We've got to be really careful. The point in Cartesian is 1 minus 1 root 2. And let's figure out what it is in spherical. Phi is not difficult to determine, but theta is the dangerous one. There are 4 possible quadrants on the xy plane for theta to be. And the sign of the quantity will give you 2 possible quadrants. So the first thing you want to do is to determine what quadrant theta has to be. That's the dangerous one. So let's look at the location of the point. 1 for x, negative 1 for y, and then root 2 for z. So we're up here somewhere. And therefore, notice that theta must be in the 4th quadrant. When we try to recover theta, we got to keep that in mind. All right, now let's check out the formulas we used again last time. We'll bring them back. X is rho sine phi cosine theta. Y is rho sine phi sine theta. Z is rho cosine phi. And also x squared plus y squared plus z squared is equal to rho squared. And that's the first thing you want to use. That's going to give you rho right away, knowing x, y, z. Right? So here, x squared is 1, y squared is minus 1 squared, z squared is root 2 squared. So we get 1, 1, 2, and that's a 4. And we choose rho to be 2 because we always take a positive rho. In spherical, we always measure distance from the origin to the point using a positive quantity. Next, we need theta and phi. Let's look at the x and y equations. If I divide y by x, then I get rho sine phi sine theta over rho sine phi cosine theta. So that's tangent theta. Exactly like the cylindrical and polar coordinates, right? Exactly the same thing. So what do we see? We see y is minus 1, x is positive 1, and here we have tangent of theta is equal to negative 1 in the fourth quadrant. This alone can put you in two quadrants, fourth or second. We have to choose the fourth quadrant. So in the fourth quadrant, what angle between 0 and 2 pi has a tangent of minus 1? 7 pi over 4. Very good. Remember, we always choose theta to be between 0 and 2 pi. Okay? Now, the last thing you can do to find phi. Now you know rho and theta. You can really use any equation to find phi. But let's take the z equation here to find phi. This tells us that cosine of phi is equal to z over rho. We know z, we know rho. Z is root 2. Rho is 2, sorry. That's 2. And we expect phi to be between 0 and pi because it's above the xy plane. If it goes below the xy plane, then we expect that to be greater than 2 pi but less than pi. Okay, so here we can see that phi clearly has to be pi over 4. Once again, remember, phi is allowed to roam between 0 and pi. Okay? All right, so that's the basics of that coordinate system. Now, but what we're really, really interested in doing is doing triple integrals in that coordinate system. We want to know what is dv in spherical. In spherical, if you consider a small d theta, d rho, and d phi, what you will end up getting is a shell, sort of a spherical shell. That looks like that. So that's a very tiny little shell in spherical coordinates. This here is d rho, a tiny little change in rho. This right here is rho d phi. Right, remember, to find the circular segment, you find the radius, which is rho, and the angle. So the angle going from here to here is d phi. The slightly trickier one here, this turns out to be rho sine phi d theta. Rho sine phi gives you the cross-sectional radius from this point, and then it spans an angle of theta. And if all of these quantities are small, this will be roughly a rectangle. If they are big, then there will be a shell, a circular shell. But if they are small, then it'll be roughly a rectangle. So therefore, the differential element in spherical, the element of that little box right here, length times the width times the height, is rho sine phi, rho squared, sine of phi, d rho, d theta, d phi. And when you do a triple integral, this is your dv. dv in Cartesian is the simplest. dv in cylindrical is slightly complicated with an extra r. dv in spherical is the most complicated one with the extra factor of rho squared sine phi. And the name tells you when is a good time to use spherical. Spherical is a good choice when the region or the volume E is a sphere, part of a sphere, or any sphere-like thing. For example, a cone. You can think of a cone as part of a sphere taken out of a sphere, right? Think of an ice cream cone as a part of a sphere removed from the big sphere. For example, suppose we started with this triple integral in Cartesian. Just look at the bounds here. X is between 0 and 6, no problem. But the fact that we got all of the x squared and y squared under root all over the place, this is strongly suggesting that we're dealing with some kind of circle, sphere-like thing. And this is a case that you want to sketch out this E that you're dealing with. If it's a sphere, then go to spherical, or part of a sphere, go to spherical. If it's a part of a cylinder, go to cylindrical. If E is sphere-like, go to spherical. If E is cylinder-like, go to cylindrical. You want to stick with Cartesian if you're dealing with a rectangle, which clearly we are not, right? These guys are not part of a rectangle. No way. No way. Okay, so let's check out what we're dealing with. We want to know if it's sphere-like or cylinder-like. Looking at the bounds here, x is between 0 and 6, and y is between 0 and radical 36 minus x squared. So on the xy plane, this is the shadow of that E. Shadow of E, the solid shadow projected onto the xy plane. We're looking at the shadow of that object. We're seeing 0 to 6 for x. And what is this? What is 36 minus x squared under a root? It's a part of a circle, right? It's actually it's a semicircle, but we're only looking at 0 to 6, so we end up looking at a quarter of a circle. Now, just looking at x and y here, it doesn't matter what we're going to be doing next. Whether we go to spherical or cylindrical, we're going to set up x and y in polar before we do the next one. Well, actually, let's hold on to that. We'll come back. Let's look at z first before we deal more with this stuff. So right now, the shadow is that quarter circle. Let's look at z here. Z is bounded below by radical x squared plus y squared. What shape is this? What shape is this? It's a three-dimensional thing, so saying a circle is not quite right. Sphere? Not quite. It's a cone. Yes, it's a cone. Top half of a cone. Because if y is equal to 0, z is equal to x. That's a straight line. If z is equal to 0, if x is 0, z is equal to y. That's another straight line. And then you got this straight line revolved around. You get a cone. So this thing is bounded below by a cone. Below. Why did I do that? Bounded above by this thing right here. And what object is this? Sphere. Yeah, half a sphere, right. It's a hemisphere, the upper half of a sphere. What do we know about that sphere? What's the radius? Root 72, yeah. And center is at the origin, right? So that's a upper hemisphere, radius root 72. Okay, seriously, people, if you have trouble recognizing those shapes, you will struggle mightily with spherical and Cartesian. Okay? So before the exam, seriously, before the exam, work on your shape. If you don't have the shapes right, you can't come up with the solid very accurately. And then you have no choice but to guess your bounds. Do you really want to guess on your exam? Not a good idea. Okay, so really work on the shapes. If you have the shapes, the bounds actually will not be that difficult. Right? Trust me. Trust me, you will want to know the shapes. Okay, anyway, now let's deal with what we're dealing with. So, we're looking at a three-dimensional object here. Whose projection onto the xy plane is a quarter circle, like that. And above this projection here, we're looking at everything inside, above a cone and below a sphere. So here's our portion of a quarter cone, and it's bounded above by a sphere of radius radical 72, kind of like this. It's a good way to think about this is part of an ice cream cone. A quarter of that. Right? You get this thing, you chop it in quarter, that's what we're dealing with. Okay? Okay, now we need the bounds. The easiest one here is to figure out the theta angle. Theta goes from here to here, right? Theta is the angle on the x and y plane. We have a quarter of an ice cream cone sitting on the z-axis. We're trapped in the first octant. So, what do we want theta to be bounded by? 0 to pi over 2. Let's look at phi. Next, let's look at the projection of this onto the zy plane from the side of that. And this is phi right here. And this line here, this is the outside of the cone. And the rounded part on the top, that's the portion of the sphere that's capping the cone. And this cone, remember, is z is equal to x squared plus y squared. Okay, so who can figure out what angle that is? Knowing this equation here, what angle is phi? What is the value of phi? Let me give you a hint. What is the equation of this line in the zy plane? Z is equal to y, right? So what's the slope? 1. Slope of 1 means what angle? 45 degrees, exactly. Slope is equal to 1, so it cuts the first quadrant in half, which has 90 degrees, right? So, therefore, phi in this picture right here must be pi over 4. Okay, so in order to accumulate everything inside this cone, we're going to let theta go from 0 to pi, swing around this way, and then z, we're going to go straight up all the way down to until we hit the cone. So start here and range down. So in this picture here, see, we'll start here, we end here. And at the same time, this gets revolved from 0 to pi over 2 by theta. And therefore, phi must be from 0, starting at the positive z-axis, down to the cone. So pi over 4. Okay, does that make sense? Okay, last one here. What about rho? How do you think rho will be bounded? Where do we start? What's the lower bound of rho? 0, yeah. Well, you want to accumulate every single point inside this quarter cone. So you're going to start here and then move out until you hit the boundary of sphere, right? This is the sphere x squared plus y squared plus z squared is equal to radical 72. And again, in order to get every single point inside that pi, you start at 0, you will go until you hit the boundary of the sphere. So the upper bound would be root 72. That's the radius of your sphere, the radius of the circle. Good. All right, so that's clearly a sphere-like thing, a cone, part of a cone. Everything is sphere and portion of a sphere. So we went to spherical. And therefore, the original integral that we started with in Cartesian, which looked pretty bad, dz, dy, dx. This is our dv, right? The differential element. And now we've gone to spherical using the bounds we just found. Now in spherical, when you set up the bounds, almost always we want to do phi very, very last. So we're going to do 0 to pi over 4 for phi. And that's a good thing that's a good rule of thumb to follow. In some of the engineering or science applications, you may want to do phi in a different order, but for all the shapes you see, again, if you don't know where to start, let phi be the outermost. The next thing we want to do is theta. And theta in this case we just saw is 0 to pi over 2. And rho is always the first one we want to do. The reason is because we can describe rho as a function of theta and phi a lot more easily than describing theta as a function of rho. Describing the radius as a function of theta and phi is a lot easier than the other way around. So we always want to integrate theta first, rho first. Rho for us is 0 to the radical 72. So here we go. And now I want to integrate dv, right? 1 times dv. And dv in spherical is rho squared sine phi, right? D rho, d theta, d phi. And there we go. And this is a lot easier to do than the Cartesian one, even though they'll give you the same answer. This, in fact, after the first round of integration, you're going to get stuck because it's just a nightmare. But this one is very easy to do after this point. Okay, let's do one more example. Triple integral over e of y squared dv. E is bounded by x squared plus y squared plus z squared is equal to 9, and y is equal to 0. Okay, again, the coordinates to use depends on E. We're clearly dealing with a sphere of some sort. That's a sphere, and this cuts the sphere in some way. So this is another ideal spherical coordinate system problem. Take a look at that, and then we'll set up the bounds for the angles and rho. This is a sphere of radius 3, right? And y is equal to 0 is the x and z plane. Actually, this cuts the sphere in two, so we got two halves. We don't know which half to find. It doesn't matter. Let's just say we're looking for the right half. Okay, if y is positive, then we're looking for the E we're dealing with is clearly this thing. All right, the right half of the sphere, radius 3. We're not just finding the volume, though. We're finding y squared over the volume. All right. Bounds. Theta. Theta goes from 0 to the back of x. So that's pi over, no, that's pi, right? What about phi? From the positive z to negative z, so we go up to down, so that's pi again. Rho, we start from the center of the sphere until we hit the shell of the sphere. So we start from the center, rho is 0, radius 3, right? So we hit 3. These are all constant bounds, so this is a really nice thing to have. And therefore, the integration will be, once again, phi last, 0 to pi, phi, theta next, 0 to pi, rho first, 0 to 3. What's y squared in spherical? What's y in spherical? Rho sine phi sine theta. So square of that is rho squared sine squared phi sine squared theta. That's our y squared. And then dv, we get another rho squared sine phi d rho d theta d phi. Okay, it looks like there's a lot of stuff here, but actually the actual integration is not terribly difficult to do, in spherical at least, because the bounds are all constant. Okay, that's it. See you next time.